Hello, I'm Simon. I've been creating a series of YouTube videos to demonstrate how you construct this animation of a scroll expander. This is in Netbeans Java. Just to show you what we're working towards, there is the expander. I'll come back to that and explain in a minute how it all works. The process of getting to this last of the four videos, we've looked at several important elements which are included in this simulation. The first one was a very simple look at time. How do you control, how do you stop and start time and potentially change the period for calls that you need to create an animation. So I created a very simple application called stopwatch. Call and reset that, run it, stop it, etc. Okay, so that's the first one we went through. The second application I put together, let's put that down out of the way. Oops. Second application went for is called animate, and it was showing the progression of different qualities of drawing and how then to animate them, starting from a very poor sort of stick view of a rather evil looking Annie, how to make it look a bit smoother and also a bit happier as it happens, how to make it look a bit more sturdy, and then how to be able to angle her arm so it always appears to be the same length. And then the obvious combination of those was put them together with a timer to run an animation and demonstrate that simply changing it, simply redrawing into every frame, every, I think, 10th of a second this was done at, you get very, very poor quality. You get flashing frames occurring. So we stopped that. We then went on to show how drawing in the background and completing the entire drawing before loading it up onto the screen gave you nice smooth graphics. Okay, so that was the second of the videos. We then moved on to, I think it's here, I'm going to have to restart that one. Went on to look at clock. And clock was a combination of the previous components, the time and the smooth animation, but it's also showing how when you've got an item you have to repeat all the time, like the clock face, which is quite compute intensive, how you can use multiple layers to build up your image and build those up in the background so you still get a smooth output. I think we, if I remember right, we demonstrated this. We also show it with the clock with the second hand running as a continuous hand as well. Okay, so that's the three build-up applications before we got to scroll. All of these applications incidentally can be downloaded both as a full zip file for Netbeans and for Netbeans development, and also as .jar files, and there's instructions on the website. I'll show you it all at the end. Okay, I'm going to take myself off the screen, and I'm now going to finally take you through this scroll animation. So first, I'd like to say just a little bit more about what a scroll is. I'm not intending to go through the thermodynamics or anything like that. What I'll do is show you that these are real devices. So this is the insides of a scroll, the two scrolls separated. This is the static scroll here. This is the dynamic scroll. Down here is the mechanism which allows it to orbit, as you'll see in a moment. And these two go together to form the closed labyrinths or pockets of gas between the two scrolls, as this dynamic one orbits, doesn't rotate, it orbits round and round like that, around the static scroll. And you can also see here, there's a hole there, that's the input port where, in our case, because it's a scroll expander, the gas comes in and the gas goes out of these ports here. The actual exit port you can't see, it's in the lid. Okay, so that's a real scroll. So to say how these are constructed, I've actually used the environment itself and some of the lessons of animation here to actually show how it's constructed. So first off, it's an Archimedean spiral with an additional central orbit. Archimedean spiral increases in radius according to how many degrees round you go. The dynamic scroll is just an exact copy, 180 degrees apart, and then displaced until you've got this orbit. So we've displaced it so it's just touching. Let me run that again to emphasize it. There's a static scroll. And the dynamic scroll is identical, but it's rotated through 180 degrees. And then it's displaced to run in an orbit. There we are, displaced so it touches the other scroll. Then you get these pockets of gas here to be able to expand outwards. And it runs, if you imagine the tip of that scroll runs around that green circle. That red cross is the actual center point of the static scroll. The center point, of course, of the dynamic scroll is being rotated around. Okay, so that's in terms of the programming of this device. You can see that if we construct first the dark grey static scroll, we can then use that construction as a set of coordinates and rotate them, mathematically rotate them to get 180 degrees and then offset them according to what point we are in the orbit. Calculating the pockets of gas, which you'll see in a moment, is a bit more complicated, but there is one key thing to realise, that every pocket starts there, goes round to there, is exactly 360 degrees long. The actual scrolls in the real system don't quite touch, but obviously we're down to the resolution of pixels here. You deliberately don't touch the scrolls. You have a film of oil running between them. You may have seen our picture, it was very oily when the scroll came apart. And just to emphasize, the dynamic scroll does not rotate, it orbits. So it stays in that same orientation. So let's run this and show how it looks. Let me take everything off to begin with. So there you have the static scroll, as it says it is static, and the exact copy, it's dynamic scroll, 180 degrees rotated, not mirror image, rotated, and then orbiting around. So its plane, if you imagine at any point in here, remains the same. It doesn't go round, it orbits. And we can show the orbits. There we go. Little red dots there show an individual point on the dynamic scroll following the orbit. And physically in the real scroll, just to show you that again, you can actually see the little pockets here which are used to maintain the orbit. And you can see they are quite small orbits. Go back to our scroll. Okay, the other complications here, you could, of course, construct a scroll and use rotation commands to move one to the other and then overlay the two together. Unfortunately, you can't easily then create the gas pockets. So we wanted to show here a pocket of gas, not from the very beginning, because that's quite complicated, coming in through the port. Let's put the port on, there's central port. It gets closed by the dynamic scroll. But we start showing the pocket from when it's at 180 degrees, round it goes, and it gets less and less bright as it goes round, showing that this is a gas expanding. And thermodynamically, this is how we do work, how we push the dynamic scroll around to drive a motor, or drive a generator, sorry. So the pressure drops as the pocket of gas goes outwards. And of course, you've got multiple pockets at different stages going out at all times here. We can also just demonstrate, let me just slow this down. So programmatically we're able to do things. Whenever we've stopped, we're able to change simulation speed. We can change the whole shape of it. The pitch, that's the distance from wrap to wrap, the thickness of the veins. There's quite a number of things we can change. We can also change pixels per centimetre. So at the moment this has been fixed on my computer to give me a real size, real centimetres for the scroll as I would see it. Of course, if you want to simulate a longer wrap, you might have to go for a scale and go to sort of half size. Okay, so we go around very slowly, slow the speed right down, and it's just coming up to the 180 degrees rotation point when we start to show the pocket of gas. The blue radius that we're showing here is really just to demonstrate that the pocket of gas is 360 degrees long. It goes, the touching points are 360 degrees apart. That's true for all the pockets and all the time. So if we were showing a second pocket of gas coming through, then we're just about to reach that 180 degree part position again. Now you see the red dot has now just got to the top here. So we could show a second one coming through. Perhaps somebody'd like to program that and show me. There's lots of things you could do to this, including making it go the opposite way to work as a compressor. And finally, the wraps get to the end, and it's open, so the colour goes because the gas then escapes, or the vapour escapes. So that's what we're trying to achieve, trying to show here. I'll now stop and go into the program environment because the main purpose of this video is to show you how all the lessons we've learned so far have been brought together to produce this dynamic scroll simulation. Let's leave that, the real scroll. Okay, so this is the code. Here's the design. And you can see here are all the objects we're using that allow us to change speeds. A lot of sliders been used here. Just very briefly, for each slider, we have events for when they've been operated. Change in number of wraps, etc., etc. Okay, some of these we're displaying as well, so we have a linked box. So if we went down to scroll pitch changed, for example, let's go and find that one. Scroll pitch changed, double click on there, and there it is. We've detected that the scroll pitch has been changed. We've then gone to pick up the value from, here's the pitch slider and get value, and then those run between a maximum and a minimum. So we have programmed in effectively constants. There aren't actually constants in Java, but the minimum scroll pitch and the maximum scroll pitch. So that's the same for all of these slider boxes that set up the scroll itself. Just very briefly, you can't have, well, it's not really constants in the same sense that there are in some other programming language, but you can use this static final declaration. So these can't be changed. So these are effectively constants, and similar to the way most people work in C, for example, they've been given capital, all capitals to show that they're constants. Okay, the point at which we activate the normal operation is, of course, the run button. There it is. So we come to the run button action performed. Very similar to other programs, we've set up timers. We set up a timer task. That timer task calls the scroll to run it, to actually run the simulation and move the points onwards. If it returns true, then this is true, we want to stop. So exactly the same format as we've seen in timer and in the stopwatch and animate examples. So exactly the same thing. You see how that's been used. A difference here is that before we set up the timer, we go to a setup routine called setup scroll. So this is more like the way we set up the clock, the analog clock application, because we know that there's certain elements we only have to do once when we run, which is to go and draw the static scroll and generate the polygon that can then be used both for the static scroll and also copied and rotated around to become the dynamic scroll. Okay, so if we go first, the usual things again we talked about here. Here we're setting the update period. Now it's a variable, comes off the slider. We do the general housekeeping of saying that once you're running, you're not allowed to change values once you're running, and vice versa. If we go to stop, there's the stop button. Same as previously for the timers, etc. Stop time equals true. This is our global flag that says I want to stop running this. Then you would say, okay, I'll re-enable I'll disable the stop button because we've now finished with it, but I'll re-enable all the other buttons ready to set it up and run it again. Okay, so there's a number of different handlers here. There is an overall handler that we saw again in the clock application where we handle that the form window has opened. So just to recap, if that's the form window, hold it properly. Can't get hold of it. There we go. JFrame, when it opens, there we go. Window is opened. We call a routine called form window opened. It's just a convenient place, a convenient way to set up the defaults for when you first open the application. So we do things, obvious things like allow the run button to be enabled, stop button to be disabled. We set up in here all the default settings for the controls. So for example, I decided we should run at 100 it's 100% the fastest speed, which gives us the minimum update period. So in fact, I think that's at the moment set at 10 milliseconds or possibly less. The default number of wraps, the default scroll pitch, the default vein thickness, etc., etc. We also allow the we also allow it to have the construction button, the one we showed you, that animates how it's built to be live, and pixels per centimeter. So everything's set up for how it appears when it first runs. These are all ones we're just talking about. They're the slider controls. But let's go past these, and I'm going to just skirt past the construction button and its wait timer, because these are specials that we added to be able to show how a scroll is built. In fact, they use bits taken from all the rest of it. So the most important thing we want to go to first is set up the scroll. We called this before we started the timer. So this is creating the static scroll. Mathematics of this I'm not necessarily going to dwell on too much, but what it has is a scroll inner volute and scroll outer volute. So these are the define the polygons that draw the scroll. So these aren't in pixel space. These are in sort of a mathematical space. So you're plotting them on a graph. You've seen before we set to a thicker pen, for example. We use the anti-aliasing on to try and get a smooth image as possible. Okay, throughout there are a number of conversions we have to go through. So I've worked in 1 degree steps of 360 degrees in the circle, obviously, but for mathematical functions we have to work in radians. So, for example, here the radian, how much the radius increases per rap. So this is the Archimedean scroll equation, if you like. You've got to increase by the scroll pitch. That's the difference between each vein going outwards on a radius over 2 pi. So 2 pi is 360 degrees in radians. The orbit radius, how much it goes round and round and round, is the scroll pitch minus the vein thicknesses minus the vein clearance. We're not allowed that to be set, actually. The vein clearance is almost impossible to see at the pixel resolution we're at. It's theoretically there. It's saying they don't quite touch. There's a space for oil between the static and dynamic veins. You can see this, as you'll see at the end, there is actually an Excel version which plots a graph and updates it continually, and you can just about make out the vein clearance on that, where you've got much better anti-aliasing. Okay, we go around 1 degree per step to create this scroll, this wrap. So again, it's the incremental angle is 1 times 2 pi over 360. So it's very laboriously telling you here, even though we could have said math pi upon 180. That's saying that this is 1 degree, 1 of 360 degrees of 2 pi radians. The maximum index, how many times we have to go round in 1 degree steps to build that spiral, that scroll, is given by 360 degrees times the number of wraps. So one of the fundamental values which determine what we see on screen is how many times round the scroll goes. I'm not going to try and explain too much about this. This is a bit of a fiddle, if you like, initial step. It's a way of dealing with the center of the scroll. The reality, you may have noticed on the picture of the real scroll, is that the very center of the wraps is a little bit different. We've just left it sort of more, we just cut a piece off it to make it work. They actually have, once you get below the orbit radius in terms of the scroll, then its shape actually changes slightly. But we've ignored that for the sake of this demonstration. So here, for each of the indices going up to scroll max, this is going around one surface of the static scroll. We work out the inner and outer volute positions. So we're actually plotting the coordinates here, and we're actually using a routine called X and Y coordinates. And let me just go to those quickly. There's quite a good explanation here because it talks about the Archimedean spiral, which is radius rate times angle, plus a vein offset here, and we include the central circle about which that Archimedean spiral is pushed out, which is the radius rate. So it's pushed out on an additional radius. So it's not a true Archimedean spiral. So that this just turns the effectively polar coordinates of angle and rate into X and Y coordinates, and plots those into a long array, which is really a polygon. It's lots of points. You could take this out, put it into Excel, plot it out, and you'd have the scroll. Having plotted this scroll, we then want to turn it into actual points on the screen. That's a little bit more complicated. You have to go around each side of the scroll to turn it into a closed polygon. with two sides to it. So we go first up to the scroll maximum index, walking our way along the inner surface of the scroll inner volute. And this is all relative to the center X and center Y, which is halfway, exactly center of the screen. We then come back the way, going around the outside, around the scroll outer volute, creating the integer set of points, which is the polygon to plot. Again, about center X, center Y. So that's it. This construction here gives you a mathematically correct scroll. This set here turns it into the nearest X, Y points that we can find and makes it a closed structure. So we effectively go out from one end of the scroll all the way around, get to the end of it, and come over the end of it, and all the way back again. So here we get to a point that we've seen elsewhere in clock, for example, which is we create a static image. So we plot these onto S, and S, we go right to the top of the declarations. There it is. S is called static scroll image. It's a buffered image, it's in memory, and we're going to put the static scroll only on that, so that can be reused whenever we like. The combined scroll image we'll see when we do the regular updates. But again, both of these are off-screen buffers that we've created, and the graphical constructs S points to the static scroll, C to the combined scroll image. And as we'll see later, we tend to use G to point to the actual screen itself. Now I had a slight problem finding where we're up to. There we go, back again. So we actually draw these onto the background screen. We clear it, set its background colour to be white. We fill the rectangle with, so it's just whited out completely. We set the colour to draw to be grey. That's a dark colour of grey, spelled the American way. We set the stroke, which we earlier on defined to be 2 points wide. We then draw the polygon. There's a reason why we do it, so you get slightly smoother output. If you draw it as a polygon first, that's as a frame, and then fill it. Doesn't make a huge difference, but it's just very slightly better quality output. Okay, so we've created the points, and these are being held globally, these X and Y points, because we'll use them to create the dynamic scroll. We've plotted those points onto this background buffered image for the static scroll that we can reuse whenever we like. Okay, we've already spoken about these two. These create the actual X, Y coordinates. The key routine to display the scroll is run scroll. So this is the routine which is called every, whatever it is, 10 milliseconds or longer. In here, we've got several things to do. We want to be as efficient as possible, otherwise we'll just simply run out of processor time, won't be able to run fast enough. So we've got no choice but to replot where the dynamic scroll is, but we can do that by copying the static scroll rotated by 180 degrees, which is actually very easy to do, because it's just once you rotate it by 180 degrees, you just sort of reflect it in both orientations about the central point, and then displace it by the orbit and the orbit position. Gas pockets are a bit trickier. We set up here dynamically the construct G that points to the actual scroll panel itself. So this is the real scroll panel. But still, to begin with, we're working on the combined scroll, the C. So we build our image, then we transfer it. So we just set all of those up to be smooth images. Same thing you will have seen in timer and elsewhere. If the global flag stop timer is true, return true that says we're stopping. There's lots of notes in here which you might find useful, so I can't cover everything. So the very first thing that we want to do is, on a combined image, is clear it, get rid of anything that's on it. This is every 10 milliseconds or so, don't forget. We then put a background of the static scroll image. So this is the value of doing this. We don't have to replot all that again. And we've got all of its values held in global memory as well as the arrays. We work out what our current orbit position is. And we then work that out into radians. As I said before, it's got to be all in radians. So then it's fairly straightforward to turn the static scroll into the dynamic scroll. I'm not going to go through this in great detail, but we basically turn it on its head, if you like, turn it right round 180 degrees. We then, and that's why the minuses are here, this is actually turning it over, and then we displace it by the orbit radius and the position, but that's the radians orbit position. So this is where, again, we talked a lot about simple trigonometry is essential. We've got to be able to turn this, decide what angle it's at, and use that to place the dynamic, the rotated dynamic scroll onto the screen. So if we were just doing this and not plotting gas pockets, it's nice and easy. In fact, we could have done it by using a rotate command as well. We then set the colour to grey and plot it. So that's it on the screen. There's a bit of mucking around here to decide whether we're showing the orbit or not. That's the small green circles that show where it's going. We also put a red dot on a single point that follows it to show how it is going around that orbit. And we do that twice. Do it once in the centre and once at the end. This bit is complicated, and I don't think I can have enough time here to properly explain it. So you either follow this or you don't. This is why we have to do this in a more complex way. So we're working out if we're at the beginning of a transit of a gas pocket. So this is saying if we're exactly 180 degrees and it's not already in transit, then we start drawing a new gas pocket transit. So we work our way through. We have a new index that allows us to look at the each gas pocket, which is because otherwise the index actual rotation only goes from 0 to 360, whereas we want to go around by the number of wraps. Oops, just lost that. I apologise, jumping around a bit here. Okay. Here, if we're just drawing a line out, that was the line which showed the gas pockets. We do actually know exactly where they start. This is why we choose 180 degrees to start the pockets. We know that from that point, the gas pocket is exactly 360 degrees long. So what we actually do is effectively walk along the dynamic pocket, dynamic index or dynamic scroll equations that we just plotted further up. We walk our way along one side of those and we come back along the static pocket, the x point, y points, which are a global variable. So that's how we actually create the polygon, which we can then fill to give us the gas pocket. There's also a bit of mucking around here to say what colour do we make it. So this is creating, rather than using a default colour, we've used a construct here called colour to create gas colour, which is a new colour based on red. So it's RGB, so it's pure red with some extra bits of fade coming into them. So the fade basically brings these numbers up from 0. If you get to all 255, 255, 255, it's white. So this is slowly whiting out, if you like. And then so we can create that gas colour to use. So every single step this is going on only if we've ticked the box to show that it's a gas pocket showing, we then fill that polygon. So I say it is a fairly complex bit of programming, particularly as business of whether you're in transit or not. We also then decide whether we're showing the central port. So we're always working here on C, don't forget, this is background, it's all in memory still. And that's the last thing that goes on is the central port, if it's required. And that's it, we've now built all the image we want in memory. And at this point, we then say, right, draw that combined scroll image onto the real visible panel. And that essentially is it. A bit of housekeeping, as previously we've seen, we then dispose of that graphical construct. We don't need it because it's called dynamically every single time we go through that routine. Okay, I don't think there's any other points that are worth going through in detail here. I've deliberately ignored these. If you want to look at these, obviously people who download this code will do, but actually they are just pieces taken from elsewhere, and I've created some weights. I've also put in text, obviously, so I've got text and a wait timer I've created, which just says, here's a bit of time to read it. So you see that sort of animation of the scrolls being drawn on the screen and moved around into their correct position. And there's some quite horrible code here to do with working out which quadrant you're in trigonometric space to work out how you calculate your angles for drawing that animation of the scroll being rotated. It's messy. If people remember trigonometry, you get things like all stations to crew. So all in the first quadrant are positive, sines positive the second, etc., etc. Probably brings back bad memories for many people. But that's what this does. It's trying to make it work properly. And again, all of these points are just picked up really from elsewhere, so you'll be able to see exactly how they work. I'm not going to go through those. That is it. You then have at the bottom end go to the very bottom, sorry. At the bottom end, you've got the main entrance. The main, as we've seen in all the other versions for the graphical user interface, it invokes the runnable code that runs the frame, and then from there on, program control is all down to pressing buttons. But we then use the event of it having been set up to just to define our constants. There we go. That form window opened. So although it's a complex program, and certainly some of the mathematics is complex, or it's not complex, it's sort of difficult to keep hold of to understand. But the principles are all there in the other simple programs, in the stopwatch, in the animate program, and in the clock, where we use there is that very important link here that we try to put as much of the repetitive elements into a routine so that we don't have to recompute those every time we call this program. And just to put that in context, I'm trying to remember what I had as the minimum update period. Wow, it was every 2 milliseconds. So it's 2 to 200. It's possible it might trip up some processes at 2 millisecond updates. That's how you get it, that fast and smooth animation. And it's turning it over 1 degree at a time. Let's just try and run that. Just thinking about it, building it. So it starts off at default at the fastest, showing everything. Remember, this dynamic scroll here is being recalculated from a copy of the static scroll equations every couple of milliseconds. I don't know if it's clear on the soundtrack, but my computer, its fan is whirring away at the moment. It's clearly doing quite a lot of work with the video recording and trying to run this. That's it. I don't think there's anything else to say. You can download this. It's completely free to download as long as it's for non-commercial use. I'd love to hear people who've extended this, turned it into a compressor version, put in extra pockets, anything else. Please do that. Do share it. Everything can be downloaded from www.redford-tech.co.uk/examples lowercase.html, or you can contact me on simon@redfordtech.co.uk. And to show that this is there's the page you'll come to, software examples. There's details here on how to get the Java runtime environment if you only want to run the .jar files, if you just want to see how they look rather than go into the projects. Otherwise, you can download the project zip files. You'll have to get your permissions right on your computer to allow it to download zip. The notes that I provided, just to show where those are. So there's a few notes that show the way that timers are set up in this environment. The screen coordinate system that's used for the graphic user interface, and some very basic trigonometry as well, are all in there. I haven't put a copy of the real scroll in. I might copy that through for you as well. But there's plenty of other examples you can see on the net. So just to go back to that, please do download those programs, or just the runtimes of them if you like. And I hope this gives you a good entry into the Java Netbeans environment. Very similar for .NET, and I'll be adding the equivalents of the .NET ones as soon as I clean them up a bit. They'll also be on the website. Oh, and I should have said that also on the website, let's get back to it, I found I had an old Excel version as well. Hopefully this will run in one go, which is very accessible. So you can actually see that the plotting out of the scroll equations. It's fun to think about it, I think. Let's just see if we can find it somewhere else. I think it's still thinking about it. Scroll simulation, here we go. I get no guarantees with this, but this gives you a bit more information about the scroll itself and its equations. You can actually see plotted out and changing as we rotate it all the actual equations for the inner and outer volutes, etc. So they're exactly the same as they are in the program, and there's a little routine here to actually run it, and shows multiple gas pockets in different colours. I've not used this for some time, so when I tried it today, I did find that you can change some of the parameters. You have to wait for it to finish its number of rotations here, so don't make that too big. But there's no guarantees with this. I think you may have to make some other changes to the graphs and so on if you want to change the sizes. But it does show nicely how it all works. That's everything I wanted to say. Thank you for listening. I hope you enjoy playing around with these different programming environments, and I'll add some more over time. At some point, if people are interested, I'll say more about the scroll and how it's used, particularly the scroll expander, and how it's used in the organic ranking cycle. Thank you. Bye-bye.